Excellent, we're live. Hi everyone, welcome back to Cambridge University Astronomy. Welcome back to Wednesday public open evenings. For those of you that haven't joined us before, every Wednesday during the winter, we have a bit of a double act. We have a talk from one of our researchers, and then if the skies are clear, we do some stargazing. It's a clear sky tonight, so after our talk, we're going to switch over to the Cambridge Astronomical Association, who are going to do some stargazing for us. Before that, we have our headline speaker. We've got Dr. Nina Sartorio, who's going to tell us all about X-rays and the bare bones of the young universe. So over to you, Nina.
Okay, so thank you very much, Matt. And hi, everyone. Thanks for joining me this evening. So I'm going to be talking a little bit about X-ray in the universe. So in this talk, I want to answer a few questions. So what in the universe produces X-rays? Why are X-rays important? And can X-rays help us understand the early universe? So first of all, it's good to have an idea of what X-rays actually are. So X-rays is just a different type of light. So as you might have heard, light is an electromagnetic wave, and every electromagnetic wave has a certain wavelength. When this wavelength is really, really, really small, about the size of an atom, that's when we call this type of light X-rays. And X-rays are very energetic type of light. That's why it can cross, for example, your skin, so that when you take a photo with X-rays, you can actually see just your bones. And I'm sure you have seen photos like this before. So you can see one here. This is the very first X-ray photo ever taken, and it was taken by this guy here who discovered X-rays, William Röntgen. And well, he kind of discovered it by accident. So people weren't really sure what to do with X-rays in the early days. So they came with lots of very crazy ideas. One of them being this apparatus here on the left. I don't know if you've ever seen one of those. These were actually used in the early 20th century to actually see how your feet were fitting inside your shoe. So basically, you took an X-ray photo of your shoe, of your feet on inside the shoe, and see if your toes are all aligning perfectly inside. So eventually, they realized this wasn't a great idea, because it gives you a lot of radiation exposure, and that can be bad for your health overall. But over time, we got better and better and better on using X-rays for medical purposes. So, like taking a photo of your arm, seeing if you have any broken bones. It's also used for mammography and other types of medical tomography. Is also used in X-ray crystallography, which is basically a way of you seeing how atoms, because the wavelength is so short, it's the size of an atom, you can actually use X-rays to take pictures on how atoms are aligning inside the different crystals or different materials. And you can also use it to just look on airport security, for example, for somebody's bag. Okay, but none of this is astronomical. So what is astronomical that emits X-rays? And to be honest, it's easier to answer what doesn't emit X-rays. So almost everything in the universe has very, very high temperatures. And all of those things that have very high temperature emit X-rays. So here I'm showing just a little sample of things that can emit X-rays. So here on the top left-hand corner, you see a picture of the sun in the X-rays. On the right-hand top corner, you see a supernova explosion, which also emits in the X-rays. On the bottom, on the left, we have just a bunch of very massive stars that are heating up a cloud, also emitting X-rays. And on the bottom right, we are seeing just two galaxies colliding, which causes a lot of X-ray emission. And on the center here, I have this beautiful image that was taken by Rosita earlier this year. And this is a null sky picture of the universe as in the X-ray emission. So almost everywhere you look, you're going to see some X-rays coming out of something in the universe. But all in all, if you take all the X-ray that are emitted, there are two main culprits. And those are the X-ray binaries, as you can see by the name. it emits a lot of X-rays, and active galactic nuclei, or what we also call AGN. Um, these two mechanisms, they rely on stars that died in the past. So usually when you have a very big, very massive star, it dies, it becomes something that is either a neutron star or a black hole. So these stars, they are formed because when a star burns all of its fuel, it explodes in this huge explosion, which we call a supernova explosion. And the core of the star itself doesn't explode. It actually implodes. It becomes very, very, very small and contracts a lot and becomes what we call a compact object, which is either this neutron star or this black hole. So for you to have an idea of what size of contraction we're talking about here, imagine that you take a star like the sun and you try to contract to this golden circle that I'm showing here. So this is a picture of London. And this golden circle is about 10 kilometers wide. And this is usually the size of what we call a neutron star. So you have to take something that's huge, thousands of times the size of the Earth, and contract it to something that's smaller than the size of the city of London to have a neutron star. So this is an incredibly dense astronomical object. And then if you want to get a black hole, then you have to get the sun and contract something that's smaller than a grain of sand. And because these objects are incredibly dense, they have an incredible gravitational pull. So they start getting material from wherever they can find around them and just start eating up all that material. They just accrete all that material into themselves. So the process is more or less what you can think similar to what you have on a drain. So imagine that you have a bathtub full of water and you just pull the plug on the drain and the water starts draining. Then it's usually going to form kind of this turbulent structure of the water, as you can see here on the picture on the left. Here on the right is an actual hydrodynamical simulation done by astronomers of the flow of matter into a black hole. And you can see that they are actually pretty similar, right? And as this material is accreting onto the black hole or the neutron star, what happens is that they lose what we call gravitational potential energy and they gain thermal energy. So this is just a fancy way of saying that they are speeding up and they're colliding with other material that's around, and they're getting very, very, very hot. And because this material is very, very, very hot, it can emit very energetic electromagnetic radiation, which is in the form of X-rays. So that's how those objects emit X-rays, is actually by accreting a lot of matter and heating up that matter so that it emits on the X-rays. Now, for AGN, for this active galactic nuclei, this thing that is accreting is what we call a supermassive black hole. So supermassive black holes, they have millions of times the mass of the sun. They are really, really, really huge. And they are usually found in the center of a galaxy, that hence the name of active galactic nuclei. And the accretion on those objects is so monstrous that sometimes they are more luminous than the rest of the entire galaxy in which they are placed. So they emit a lot of radiation, and they're very, very bright. Today, these AGN are actually the main emitters of X-rays. But I studied the universe a long time ago, just a few 100 million years after the Big Bang, which sounds a lot of time, but for a universe that's 14 billion years old, that's actually not that much. So what happens if we, turn the clock back 13 billion years? Well, because AGN, they rely on the supermassive black hole, you have to have a supermassive black hole around to have an AGN. But that's not necessarily the case 14 billion years ago, because we probably didn't have the supermassive black holes, because supermassive black holes, they don't just exist out of one star. You have to have lots and lots of stars that have died, and they have to merge with each other. Like you can see, for example, on this merger tree here on the right. So you have a lot of smaller black holes that combine to create a slightly more massive one that then combines with another one to become slightly more massive, until eventually, given billions of years, you can actually create these supermassive black holes we see. So if you go 14 billion years ago, there weren't any supermassive black holes, and therefore you didn't have any AGN. Therefore, we think that in the very beginning of the universe, the only thing that could emit really humongous amounts of X-ray radiation were these objects called the X-ray binaries. Now, how do these X-ray binaries differ from AGN? Well, they have some things in common. So the first thing is at the center of the accretion disk, you can have a black hole, but this black hole is usually just a few times the mass of the sun, rather than millions of times the mass of the sun. Or it can also be a neutron star, which is not true for AGN. And the other main difference is that this neutron star or black hole, they are not alone. They have a companion star. So that this two star, the star plus this dead star, form what we call a binary system. And because the neutron star and the black hole have such a strong gravitational pull, they can actually start eating up material from the surface of its companion star to form an accretion disk and then emit X-rays. So what I'm going to show you now, it's a little simulation from that is related to the work I've done. So here what you can see is two stars, and one of the stars now, the more massive one, evolves more quickly and it becomes a super red giant. And then eventually it explodes in a supernova explosion, and you're left with this small neutron star. Now, when the other star evolves to a red giant, then the neutron star suddenly can grab this material from the surface of the companion star and create this accretion disk around it. And this accretion disk can then emit lots and lots and lots of X-rays. And this is the way that we think X-rays were mostly produced in the early universe. Okay, but why is this important for the early universe? Why should I care about X-ray binaries at all, if they existed or if they didn't? Well, let's recap a little bit about the early universe. So you all know that we had a Big Bang, and when the universe formed, and when at those very early times the universe was very, very hot, and eventually it expanded and it cooled down, and we were left with a lot of hydrogen and helium atoms, but they were in a state that we call neutral. Okay. And there weren't any stars in the universe. So the universe was completely dark and is what we call the dark ages of the universe. Okay. Eventually, a lot of gases started to get together due to gravity and became more and more and more dense. And in some regions, you started forming a few stars. So those were the very first stars the universe ever saw. And these stars started emitting radiation, so they were starting to shine light in the universe finally. And this is what we call the cosmic dawn. Now, one very important thing that the stars started to do is to change this neutral universe full of neutral atoms into a universe that, as we call it, is ionized. Okay, so what do I mean by that? So if you imagine here on the left, you have a neutral atom. So a neutral atom has one proton in its nucleus and a little electron here in green that circles around it, more or less. If you have radiation that comes from these early stars, this radiation can interact with this electron and kind of kick it out. And then you're left with an electron on its own and a proton on its own. And then this proton on its own, it's what we call an ionized, in this case, hydrogen atom. Okay? Now, the important thing here is to realize that you started with some light and you were left with no light, right? You were left with two particles, with one particle traveling faster than further away from each other. Okay? Now, Why does that matter? That matters because if you had a star in the early universe, that star would start shining radiation, right? And if the whole universe was neutral, then this radiation would just interact with one of those neutral atoms, and then you wouldn't be able to see that radiation because it would just disappear. It would go into ionizing the atom. So the universe was completely opaque at this time. And then, as more and more stars came along, then more and more the universe was ionized, and then more and more the radiation could actually traverse through the entire of the universe and get to your eye. And then you could actually see a star that's far away. So if the space between stars and between galaxies was all neutral, we wouldn't be able to see anything in the night sky. The fact that we can see things in the night sky means that the space in between, for example, the sun and the next star, is vastly ionized so that light can come through. Okay? So basically, we have this transition from the dark ages in which the universe was opaque to a universe like today that's mostly transparent. Okay? Uh, so this created what we call the Swiss cheese model of ionization of the universe. So what we think happened is that you have all the stars and they started making these little bubbles that are ionized within the universe. And the reason why we think those were little bubbles is because most of the radiation that those stars emit, they can't travel very far. Like most light can't go through your skin, um, the light from these stars could only travel a certain length until they got absorbed by these neutral atoms. And then you would form these little bubbles, and these bubbles would eventually expand more and more as you got more and more stars until the universe is fully ionized. So if you look at this video again, so you start with this box that's completely opaque, and then more and more stars make these bubbles, and these bubbles become bigger and bigger and bigger until eventually your universe is fully ionized and transparent. But ionizing the universe this way takes a very long time because you have to wait until these bubbles get bigger and bigger and bigger. And observations, they hint that this should have happened more quickly. So how could this be? So one answer is basically just using X-rays. So if you had these X-ray binaries in the early universe, the X-rays could actually get out of the bubble. So yeah, don't do that now because of Corona. You should never get out of your bubble. But X-rays, they were able to get out of this bubble of ionization that was done by most of the other stars' radiation and actually start reaching these middle bits of the cheese in between the bubbles. This is what we call the intergalactic medium because it's the space in between galaxies. And then it started melting or ionizing this intergalactic medium before the bubbles got to that size, and that made easier for the bubbles to expand. So it made this ionization of the universe, this process of making the universe transparent, a lot quicker. This was also very dependent in the early universe because not every single place had an X-ray binary. So what you would have is regions of the universe in which the intergalactic medium would be less ionized, and then in a region where you would have a lot of X-rays, this intergalactic medium would be more ionized. But either way, X-rays start opening the way for a transparent universe. And X-rays have another important role to play in the early universe that regards the star formation. So just recalling how star formation works, usually you have a big diffuse cloud of gas, and this cloud, because of gravity, starts contracting and become denser and denser and denser until it becomes a star. Now, the problem is that as a star contracts, just like I explained with the accretion disk, it becomes hotter and hotter and hotter. So imagine that you start with this yellow molecular cloud here, or cloud of gas, If this contracts to the orange one in the middle of the screen, then it's hotter. Now, hot gas, it exerts a pressure that opposes gravity. So the hotter your gas, the harder it is for you to contract it, okay? And then if you don't have a way to cool, this gas is just going to become hotter and hotter and hotter, and it's going to be stronger and stronger and stronger in opposing gravity until gravity can't do anything at all. And then you just stop contracting. But if you stop contracting, and you can't form a star. So it's very important in the early universe that you have something to help those clouds that are contracting to cool to actually form new stars, okay? Now, in the early universe, this role is mainly played by what we call molecular hydrogen. So molecular hydrogen was the main thing that acted into taking away this heat by radiating it away. So as long as you had a high amount of molecular hydrogen in the early universe, you could cool and you could continue contracting until you form the star. So basically, if you want to resume this in the slide, if you have a lot of molecular hydrogen, that's good. You can contract, you can cool, you can form a star. If you have very little molecular hydrogen, then that's bad, because it would mean that you wouldn't be able to contract your cloud and you wouldn't get any stars. And how do X-rays help us in that then? Well, remember when X-rays ionized stuff? Okay, so X-rays continue doing that. And because they are very good at traveling through very dense media like they do through your skin, they are able to create lots and lots and lots of free electrons. So these electrons that kicked out of the neutral atom. And you end up with a lot of free electrons in your gas. Now, these free electrons, they actually help two hydrogen atoms to combine into a hydrogen molecule. They're what we call catalysts. So they basically take two hydrogen atoms and make them hold hands, but then at the end of the process, they just become free again. Okay? So by having a lot of X-rays, you are able to increase a lot the amount of this molecular hydrogen that is found in the gas. And because you're able to increase the amount of molecular hydrogen, you're also able to create a lot more stars. And then if you create more stars, you are able to create more radiation that helps us again into making the universe transparent. So X-rays were vital for the early universe because they not only made it possible for stars to form, but also because they helped the whole universe be ionized. And that's basically it. So I'm gonna take questions.
Thank you very much, Nina. That was fascinating. So like I said, any questions, I pop them in the YouTube chat just while people have a think about questions. Can you talk a little bit about like the blend of like theory and observation? Because I know some astronomers like to go and use telescopes and look at the universe, and some astronomers like to go and simulate things inside computers, right? Can you talk a little bit about what your approach is with those two things?
Yeah, so because this is from the very early universe, we can't really see anything from those times. So most of what we rely upon is on big computer simulations. So what I do is I use basically a supercomputer to simulate how the universe would look like at those points in time. And then we can compare them to observations of what we do today, because depending on how the universe was in the past, it affects the whole of its evolution to see how it is today. Okay, so for example, if you didn't have enough X-rays in the early universe, you would expect, for example, radiation that is arriving on your telescopes right now to look sometimes slightly different. So there is this one radiation that's called the 21 centimeter line. And this is a line that is emitted when, so imagine that you have a hydrogen atom. When it flips spin states, so this is just a property of an atom, it emits a little photon. And this photon, just like I was explaining in the talk, it interacts differently with neutral gas to ionized gas. So by just looking at this signal, we can say, oh, okay, the universe was all ionized by this time. And then we have to find a way of explaining how we get the universe ionized in such a period of time. So yeah, I hope that makes sense.
Yeah, it does. Yeah, so we have a couple of a couple of comments coming through saying they thoroughly enjoyed it and they thought people think the animations were particularly impressive. We do have one question from Selsa, who wants, first of all, says it's fascinating to hear about X-ray binaries, and wants to know what else can we learn about the early universe using X-rays.
So mainly is knowing how. So, for example, if you use by knowing how much this X-ray binaries, how many of them existed, you can, for example, predict how many stars you would expect to form. Because if you didn't have these X-ray binaries at all, you would expect a lot less stars to form over time. And these reflect on the whole properties of stars that existed in the past. So, for example, the stars today, they are mostly stars that have the mass of the sun. So the sun is the most boring star you could think of. There are millions and millions and millions of stars like the sun. But in the early universe, it was actually very hard to form a star like the sun because the sun is very small. And because you didn't have a lot of other of ways to cool this cloud of gas when stars were forming, um, you relied on just this molecular hydrogen, which there wasn't a lot of to begin with. So the stars at the beginning of the universe, they tended to be more massive. And if they were more massive and we were able to form them via this, because of these X-ray binaries, then they would create a lot of little black holes and little neutron stars, which eventually would merge to form things that we see today. Now, there is, when these things merge, when little black holes merge and little neutron stars merge, they emit something that we call gravitational waves. And this is something that we can measure. So one of the things that we have seen that are maybe the closest thing to an early observation of stars, uh, of stars in the early universe, are these gravitational waves that are detected by LIGO. So what they see is they see these smaller black holes that are more massive than what you would expect from something that we see today, um, that are merging with each other. So basically, by seeing how many of those things we can detect, we can have an idea of how many stars have formed and how many X-ray binaries you had. And vice versa, you can make models to see what fits observations and what doesn't. So in overall, it just helps us have an idea of how the stars in the early universe look like and how many of them existed and how they affected the whole universe that came after that.
Excellent, thank you. One final question, a bit closer to home than astronomical. Do you know if lightning emits X-rays? Asks GT Telera.
I don't think lightnings get anything close to the temperature you need for emitting X-rays. So they do manage to ionize things when it falls, like around, and heat up a lot of the gas. That's why you hear the thunder. So that's just the expansion of the gas around the lightning that creates the noise. So it's basically pushing all this air away. But it doesn't get hot enough anywhere for you to actually produce X-rays.
Right. So I think so that's completely right. If I remember, I think you do get X-rays coming out of thunderstorms. It's not because of the lightning itself, like Nina said, it doesn't get hot enough, but the process that makes lightning has to build up an electric charge inside the clouds, and that can like accelerate electrons. And when those accelerated electrons go into the air, I think you get X-ray showers. Like I'm sure I've seen photos of thunderstorms taken in the X-ray, and they look pretty cool. So you do get X-rays coming out of thunderstorms, but like Nina said, it's not because it's not the actual lightning because that doesn't get hot enough. Oh, okay. Questions coming in. People have found the chat box. Timothy, aged 8, wants to know: is thunder and lightning X-rays coming from space? I guess that's talking about. I'm not totally sure what that means. I'm sorry. I guess the answer: do X-rays come from space? Is maybe that's the question.
I think he's asking if X-rays from space cause thunder.
Oh, yes. Okay. Yeah. Yeah. That makes a lot more sense.
So no, X-rays don't cause thunder. And one of the very nice things about being here on Earth is that, so as you know, X-rays are not very good for you, because if you get a lot of X-rays, then that can start messing up with your cells, and then they can become sick, and you can get lots of different illnesses, including cancer. So that's why even if you go to a doctor, he's not going to take a lot of photos of you in the X-rays, because that would eventually make you sick. So you can do it, but only in small quantities, a little bit every year, but not all the time. And the Earth its atmosphere has this amount of gas around the Earth that actually protects us from the X-rays that come from space. So even if the space is all emitting a lot of X-rays, the Earth is sheltered from those X-rays that come from space. They never even get near you. And that's good, because otherwise we wouldn't be able to exist. Now, for me, and for other people that study X-rays in space, that means that we can't just put a telescope here on Earth and just look at X-rays. So we usually have to send something to space to take a picture of the X-rays, because there you don't have this atmosphere protecting us anymore and sheltering us from the X-rays. So you can just take pictures in the X-rays if you send something to space in the first instance. So.
Right, and I think so that probably leads on to the next question from Daniel Vaswani, who talking about amateur astronomy. So he says amateur astronomers, as well as observing visible light, can also observe in the radio and observe some infrared wavelengths. Are amateur astronomers able to observe in the X-ray? And he does say, feel free to get technical.
No, so unfortunately, if you're doing things from the ground, you really can't get around into taking pictures of space in X-rays. There are some balloon experiments that you can get high enough above the first layers of the atmosphere. So as long as you are above the troposphere and the exosphere, then you should the stratosphere, sorry. Then you should be able to start being able to see increasingly more and more and more X-rays coming from space. So I guess if you are a multimillionaire and you're bored, then you can always get one of those meteorological balloons and attach a very, very fancy camera or telescope to it with a film, and then take a picture in the X-rays of something. But yeah, it doesn't work for us here on Earth, and for any normal person anyway.
Excellent. Well, thank you so much, Nina. That was absolutely fascinating. And there's a nice link. So speaking of amateur astronomy, we're going to switch over to our amateur astronomers now, the Cambridge Astronomical Association, who I have my fingers crossed are still looking at some clear skies. Is that right, guys?
We are. I've got a
thumbs
lovely
up.
clear
Wonderful.
sky here for you.
Very exciting. In that case, so virtual round of applause for Nina, and over to the amateurs for some stargazing.
Okay, thank you. Bye.
Right. Thank you very much. Okay. We're going to be looking at the area around Pegasus, which is more or less directly overhead at the moment. And one of the things in Pegasus is a globular cluster. It's called Messier 15, and we've got it on the screen now. Yes, Paul?
Yes, Brian. For once, I've not gone off piste. I've done
Good.
what you asked me.
That's good.
So that's the globular cluster Messier 15, and it's a 4-second exposure. So that was just a sighting shot. I'll trigger off a longer exposure for you while you do the commentary.
Okay. Right. Right. These globular clusters hover around the Milky Way, and there's about 150 of them. They're like tiny mini round galaxies. They're got about several 100,000 stars in them, and they're very compact. And this one is about 175 light years across. Now you can see that Paul's increasing the exposure, and we're starting to see the stars around the outside. But you can see the center of this particular globular cluster is very, very bright. And that's because it's called a core collapse globular cluster. Over half the mass of this of the stars are within a 10 light year radius in the middle. And what's happened, the core has collapsed under gravitation and formed a black hole. But it's not the usual sort of black hole you get when stars are formed. There are few solar masses, and it's not like the supermassive black hole you find in the center of galaxies. There are many hundreds of millions of solar masses. This particular black hole is about 4,000 solar masses. So it's an intermediate black hole, of unusual sort. The other two, the stellar black hole and the supermassive black hole, are more common. And globular clusters are very, very old. And this is one of the oldest globular clusters, 12 billion years old. And it also has a planetary nebula in. Last week we looked at some planetary nebula, and again later today we'll look at another planetary nebula. And these globular clusters shouldn't have planetary nebula in. And what's probably happened, as it was orbiting around the Milky Way, it's captured a star which has evolved and then shed its outer layers and formed this planetary nebula. So we can surmise that it did come quite close to the Milky Way in some stage. Do you know which way is north, Paul?
Not really, you know.
Right, I think I can see it. Can you zoom in on this?
Now you're asking.
I like to set a challenge.
Let's see if I can make it any bigger for you.
Yeah, please.
With this camera.
Oh, is it going to cause you problems?
Well, let's see what happens if I do this. Does that make it any bigger for you?
Let's go. It's getting bigger.
Or is that the same? That's about as big as I can get it, I think.
Yeah, okay. Right. Not to worry. That
carry on, and I'll see what else I can do.
The planetary nebula, I was hoping it was going to be on a bigger scale, and we might have been able to see the planetary nebula.
No, I've got my telescope in. My telescope's in short focus, wide.
Right, no worries.
F5, you know.
No, that's no problems. The Planetary Nebula is about just outside the nucleus at 11 o'clock, but it's just beyond our range at the moment. But these, as I say, are very, very old clusters. The clusters we find inside the Milky Way are the open clusters. We won't be looking at any of those tonight. Okay, I think we're just about there. And now we're going to go over to Swaffham Prior and Mick, if you're ready.
Yes, I'm ready. There we go.
Hooray.
Are you seeing it?
Yes, we are. Thank you.
I'm just going to make this a little bit smaller. Right. Where would you like me to go? You tell me.
We left with Copernicus last time we looked at the moon, so we'll have a quick look at Copernicus, and then we'll go up towards the moon, up towards where you are. So start at Copernicus. That's where we left off.
Tell me when to stop.
There we are. It's coming into the middle now.
I'm afraid the atmosphere isn't very good tonight, so I'm
no, that's okay.
Let's try the focus again.
Yeah,
that's about as good as I can get, I think.
Yeah, we can see it's wobbling about a bit. Right, to give you a scale, that's just 90 kilometers, that crater, and a comparatively young crater at 800 million years old. And we can see in the center of the crater, there are some mountains, and they're about 1 kilometer high. And what happens when an asteroid hits the moon, it behaves like a liquid for some of the time, and the center of the crater rebounds and then freezes, and that's what or cools down, and that's what the central mountains are. They're the end product of the impact as it rebounds and then sets. So many craters do have central mountains, and if you look at some of the other craters, the one in the bottom corner, bottom left corner, you can see has also got craters. And this is a comparatively young crater. Now we're in the ocean of, in the Sea of Rains, and we'll head upwards to the Bay of Rainbows. And that, just if you stop there, you can see an arc of mountains at the bottom middle. There we are. That's where some of the tallest mountains on the moon are, in that Apennine mountain range there. Then going round the Sea of Rains, we see the flooded crater of Plato, and then a much larger impact, the Bay of Rainbows. Now I was going to have a go for a volcano, because the early observers, obviously when they saw craters, thought they were volcanoes. And there are about 300 volcanoes on the moon, but they're very, very small, only just a few kilometers across. All the craters you see are not volcanic, they're impact craters. So do we want to have a go for this crater? How large can you zoom in?
Quite a way, yes.
Go on then.
Tell me.
If you go to the left side of the Bay of Rainbows.
Left.
Yeah, that's it. Pull it into the middle. To the left, you increase it. Let's see what we can see. We'll see if we can see it. Maybe a bit too much. That's it. Now drag it across to the right
it's all right.
And no, that's go the other way. Sorry, that's it. Keep going.
Is that it there?
Right. No, it's just a bit to the left. Keep going to the left with your cursor. You're nearly there. Keep going to the left. There's a little light patch.
There?
Keep going. Next light patch on the left. That's it. Down a bit. Down a bit. That's it. No, that light patch. Go back to the right slightly. That's it. There. And that is one of the 300 volcanoes. It's. Can I see it clearly? That's it there. Yes. Sorry, I was pointing at the wrong thing, but you've lightened it up now. It's very indistinct. It's about 20 kilometers in diameter, but they're domes. They're volcanic shield volcanoes, and so they're not very distinct and don't cast much of a shadow. So it's just above those two craters where you were pointing. And that's the largest volcanic dome on the moon. Sorry?
There is a dome there.
No, it's not that one. That's just a wrinkle ridge. You've got ridges on the lava because the basin, the impact basin, was caused by a massive impact and then has flooded with lava. And then during the cooling down process, it's sort of wrinkled, and you've got these wrinkle ridges that you can see. Right, we'll work down towards reduce the scale, and then we'll work down towards we'll go down the terminator. Right. Just go up a bit. We're going to be on the left side of the moon, so you might have to increase the brightness. Now drag it across a bit so we can see.
Okay.
Yep. And I'm just getting my bearings. I was after Gassendi.
Are we there? I don't know.
Right, yes. The crater in the middle is called Bullialdus. Let's get it right. And it's about 60 kilometers across. And there's a valley that leads to the left, going up at an angle at about 11 o'clock. More horizontal. And you'll see a bridge going across it about 2 diameters away. There we are, it's near the top. Some observers, when they saw this, can you point your cursor to go to the left, and then keep going, then go up to that causeway. Yeah, some observers, when they saw that across the shallow valley, there's a shallow valley leading from the crater, they thought it was a bridge or a causeway, but it's not. It's just a cliff area, and that's you can see the atmosphere is causing problems with our images. But going back to Bullialdus, it was found that in 2008 that it had water, or indicators of water, in the central mountain of Bullialdus. It was discovered by a NASA instrument on board an Indian lunar orbiter. It was called the Moon Mineralogical Mapper, and it identified that there was water in the central mountains of Borealdus, but nowhere in the rest of the crater. And of course, we know the central mountains come from deep within the moon's crust, and so it indicates that the presence of water could be beneath the surface. Right, and we're just going to carry on down to where shall we go now? Just beneath, where are we? Just right at the terminators, you've got three craters together. There, that's it.
Let me enlarge.
Drag it across.
There we go.
Yeah, and we've got three craters there of 3 different ages. So this is how we determine the age of the moon. It's just beneath the area, the dark area, called the Sea of Epidemics. You find that the moon has a good side and a bad side. The right-hand side is the gloomy side. You've got the lake of death, the lake of happiness, the ocean of storms, the marsh of rot. And over on the other side of the moon, you've got the good stuff. You've got the lake of happiness, the sea of tranquility, the lake of joy, sea of serenity, and that sort of thing. So we're on the gloomy side of the moon. And then we'll just finish as we go towards Tycho at the bottom of the moon. There we go. And this is even younger than the Copernicus. And the ejecta from this, the stuff that came out during the impact, it hasn't had time to darken because it's a very young crater. It's only about 100 million years old. So it was formed when the dinosaurs were clumping about. But as far as the moon goes, that's very, very young. And we can see the ejecta actually goes more than half the way moon, radiates more than halfway around the moon. And you can pick this up in binoculars. You can see on a full moon is very good for showing the ray system. Okay, then we'll stop there and we'll go over to David in Halton.
Hello. Okay.
Can you hear me?
Yes, we can hear you. Have you found?
You can't see me. Oh, there I am.
Yeah, we can see your hand. Right, we set David a challenge, but unfortunately there was a supernova not very far away from the constellation of Pegasus, but David had a go, and the supernova is just too close to the bright nucleus of the galaxy to be seen, and also it's right beside the moon, which is causing enormous problems. Yeah. So we've given him a backup object of a galaxy. Have you got it?
Yes.
Good. Let's have a look.
Okay. This is NGC 2403.
Yep.
Not showing awfully well. The sky is quite bright.
Yeah, no, it's the moon causing problems.
When I switched on tonight, I discovered both my cameras were dewed up.
Oh, right.
And Windows decided to do an update. So
yeah, Paul had that trouble as well before we came on air. So, but this is a nice spiral galaxy in Camelopardalis. That's the constellation of the Giraffe, not very far away from the Pegasus, and it's not a very bright constellation, just a few dim stars. But this is a comparatively close galaxy. It's outside our local group at about 10 million light years. But one of the things we'll be showing you later in the season is, of course, the Orion Nebula, which is a gas cloud, a cloud of gas and dust that you can see quite easily with the naked eye and is good in binoculars. This cloud of gas and dust is about 25 light years across. But there are bigger gas clouds, and one of the biggest is in the Large Magellanic Cloud. That's a neighbouring galaxy in the southern hemisphere. And there is a great nebula, many times bigger than the Orion Nebula, called the Tarantula Nebula. And it's 1,000 light years across. And if you were to put that where the Orion was, it would be so bright, you'd be able to see shadows at night. But this particular galaxy has got enormous gas clouds, and we can see some of them. There are one or two bright stars in the galaxy, the two bright ones, they're just stars, but the other blobs, yeah, and go up towards that other star, one there, and then one the other side, blob the other side of that star, keep going to the left, keep going left, keep going left, now there, that one. That's a gas cloud we can see in another galaxy, and that's truly enormous. It's over twice as big as the Tarantula Nebula, and that's it. We can see it better now, and you can see there are other faint blobs as well, and there are over 100 large gas clouds in this galaxy. It's not a very big galaxy. It's only about half the size of our Milky Way. And so it just shows you how big these H2 regions, as they're known, they're all around here. Yeah, you can see dozens of them. The more you look, this has got, as I say, over 100 of these large H2 regions, these gas clouds that are being lit up by star clusters. Good. Okay. Thanks very much. And we're coming to the end now, and we'll go towards Paul, who should have a load of galaxies.
Yeah. Hi, Brian. Just get that shared for you. This one here, isn't it? There we are. It's not the most fabulous image that I've ever taken of this particular object.
No, don't worry.
You can see the main galaxy in the middle there.
Right.
And if you use your imagination turned all the way up to 11,
yep,
you can make out some of the others.
Right.
Just about here.
Yeah, there are 4 galaxies just above it. I can see some of them. Yes, you can see a line of them just above the galaxy. If you bring your cursor down,
yeah,
there we are.
There,
just to the left a bit and up there, and you've got a row of them, 3 of them in a row going down.
Yeah.
Well, one of them going downwards. That's it. They're more distant galaxies. This galaxy is about 8 times. It's about 4 times further away than the galaxy we've just looked at. But it's got a very curious feature. You can see the central bulge. We can't see much of the spiral arms because the sky is lit up a bit. You're suffering from light pollution there. But this galaxy is very peculiar in that normally spiral galaxies, the nucleus rotates the same way as the spiral arms. But this particular galaxy, the nucleus goes the opposite direction to the spiral arms. And there are just a few galaxies that do this. And the favorite theory as to why it does this is that it's swallowed another galaxy, causing the nucleus to disrupt and the spiral arms are counter-rotating. So that's that. And nearby is another group of galaxies. Which do you want to try for it, or shall we not?
Well, I've got
Stephan's quint.
Yeah, there's one here.
Stephan's quintet.
Yes, I was trying to work out. I mean, that's supposed to be in the same field of view somewhere.
Yeah, it's over to the left, below those two stars.
Here?
No, there's two more stars to the left. That's it, down the fraction. Yeah.
Down here somewhere, is it?
Yeah, it's just below that area there, but I can't see them.
Yeah.
There's a
big
sky
dust bunny just there. That's why.
Yeah. It's just too dark, but never mind.
But they are 300 and something million light years away, though.
Yeah, they're about. They're sort of 8 times further away than the counter-rotating galaxy. But I just thought it was the first group of galaxies to be discovered. I thought we'd just have a quick look at that. But
I think with my other camera, another time we could do that.
We'll come back to these when the moon is not about.
Yeah.
That's good. Right. I think we've just got a planetary nebula to look at, which we'll finish with. Is David found it yet?
Okay, I've just slewed to it. I'm not entirely sure what I've got in my frame. Brian will be able to tell us, I'm sure.
It's the blue snowball planetary nebula.
Is this it here?
Let's see. Give it a whirl. And this is how...
Let me...
This is how our sun will end up. We saw with stars bigger than 8 solar masses, when they die in a spectacular supernova explosion. And once they've, all that's left over is either a neutron star or a black hole, as you heard in the talk. But stars under 8 solar masses, when they die, they run out of hydrogen to fuse into helium, and the star swells up into a red giant. And then it puffs off the outer layers. Stellar winds blow out the outer layers of the star to form a planetary nebula. And hopefully, here we come.
David, have you intentionally not yet? Oh, there we go.
Here we go. Oh, you've got condensation problems as well.
Oh, yes, very much.
Yeah.
I'll show you just briefly the Images horror story.
Yeah, we can see there are 3 large, well, 1 small blodge and 2 larger blodges.
This is my other camera, still drying out.
Yeah. Because it was totally cloudy, sort of half an hour before the talk started, we weren't really prepared.
Indeed,
but
exactly that. Let me see if I can find a guide star. Keep this thing in the middle. There we go. I'm doing, let's reduce the exposure time. restart. So what I am doing is 20-second images, but stacked. So we should see the image develop as we watch.
Oh, right. So can you zoom in a bit,
Yeah, this is
please?
a blurred image here. Let's see what we get. That's better.
That's it. Good, it's coming. And we can see that the outer shell of the expanding planetary nebula. Of course, they're called planetary nebulae mostly because they're round and absolutely nothing to do with planets. But that's how our star will end. And these planetary nebulae only last maybe 10,000 years, and then they get so faint and they disperse into the interstellar medium. But planetary nebulae are very difficult to tell the distance to. So we just generally say they're a few thousand light years away. You can't really tell how big, how far away they are. And right in the middle is a white dwarf, and that's all that's left of the star that's puffed off its outer layers. And this star right in the middle, which we can't see.
I do wonder if I've got a bit of condensation here. And,
yeah, it's not as sharp as it.
It's not.
The star images aren't sharp.
They're not. They've got little halos around them, which is.
Yeah, I think we've got condensation.
Yeah.
Normally, well, we come back to it. Normally, we'll be able to see the white dwarf in a planetary nebulae, and these are some of the hottest stars you'll see. This particular one is over 75,000 degrees in temperature. And what they do is just then spend the rest of eternity cooling down. They've finished the nuclear processes, nuclear fusion, and they're just cooling down. So that's the death of a small star like the sun, all the way up to a 8 solar mass star is one of these planetary nebulae. And there are many hundreds of them in the night sky. So we'll find some more later in the year. Okay, we've come to the end of our time. And despite one or two complications, thank you very much to our telescope operators who've had to get things up and running very quickly when we suddenly decided to go for it. So thanks to Paul in Halton, Mick in Swaffham and Paul in Over.
And David in Halton.
David in Halton, sorry. I can see you.
Got us mixed together there.
Yeah, I did.
Not to worry.
Yeah, sorry about that. Okay, thanks very much. And I'll hand you back to Matt.
Wonderful. Thanks so much, guys. Thank you to Brian as well. You didn't thank yourself, but thanks for the for the commentary. And thank you to Nina, of course, for providing such an excellent talk. We will see you all next week. So same time next week. Bye-bye.
Bye.